Hello everyone, and thank you very much for joining us today for the Optics.org webinar on DLC coating challenges and chalcogenides. This webinar is presented by Ray Pini, who works for EMF, a dinosaur company. Ray's been in the optics and photonics industry for over 25 years, and for the past 15 years, he's been involved with the design, manufacture, and commercialization of infrared optics with a specialty in chalcogenide optical manufacturing. Before we start, I just want to make sure we have everything working properly. We have a questions box. Please feel free to use that throughout the duration of the presentation. We'll be coming to a Q&A session at the end of Ray's presentation, and we'll try and get through as many of those questions as we possibly can. Of course, if we can't answer every question, don't worry, because a representative from EMF will be getting back to everybody at the end of the presentation over the next couple of days. Additionally, we're also going to be carrying out a couple of polls during the presentation as well. Now, these give you the opportunity to engage with some of the questions we have and also help to put together some of the more Q&A session and actually bring it together and focus it around some of your applications and challenges as well. So with that done, I'm going to pass over to Ray and ask him to join us so we can kickstart today's presentation.
All right. Thank
Ray,
you, Robert.
over to you.
Nice to see you too. All right. So thank you and welcome everyone. Be talking today about overcoming DLC coding challenges on chalcogenides. And just wanted to start with a quick introduction to EMF. EMF is a dinosaur company, and we have been a thin film coating manufacturer since 1936. We're coming up on our 85th anniversary. And we're a demonstrated leader in optical coating solutions. We've got a large technical team and a lot of design expertise to help overcome almost any coating challenge. We do have two facilities. Both are ITAR registered in ISO 9001. One is in Rochester, and then our corporate headquarters is in Ithaca, New York. We have some special capabilities. One is to be able to coat optics up to 108 inches in diameter. And we have over 40 million square inches of annual coating capacity. So today we're going to talk about infrared optics and specifically some of the coating challenges that occur with infrared optics. One of the things to note is that infrared optics tend to get used in some of the harshest environments in the world. They range everything from driver vision enhancement, which is basically putting a thermal camera in front of a car, to the defense world, where they're operating on ships and aircraft and protecting our warfighters. Search and rescue, where thermal cameras are hanging off the bottoms of airplanes and helicopters. And finally, probably the most difficult environment is firefighting, where these cameras are actually going into fires and helping firefighters see through the smoke to find both people and where the fires are still burning. So just to get things started and get everyone sort of warmed up, we're going to have a quick poll. Tell us a little bit about your application and what you try to do with infrared optics. Robert, can you have a little difficulty seeing the poll results? If you could let us know what the results are there.
Sure, absolutely. So we've got a large group of you people coming from, unsurprisingly, the defense industry, with 60% of attendees coming in from the defense. We've got 4% coming from the automotive industry, 19% from looking for industrial applications, and 17% coming from the scientific community.
Okay, that sounds about right. And most of my dealings with over the years, majority have come from the defense industry, and well, all are important. The defense one is some of the most challenging cases out there. So I'm going to talk a little bit about why infrared optics are coated with diamond-like coatings. Basically, the key factors for diamond-like carbon are an extremely high hardness, excellent abrasion resistance. So basically, you can clean the lenses. Any sort of materials being blown into the lenses won't damage the lens system itself. In addition, it's very resistant to chemicals and other types of corrosion. So it's resistant to salts and particularly useful in naval area. But more importantly, it's also completely optically transparent in the infrared. It's got a couple other features, like it's biologically compatible, it's an electrical insulator, and does have low friction. Okay. And so what is diamond-like carbon? It's actually a let me get back to my discussion. A combined form of graphite and diamond, and it's very well suited for the infrared, mostly because it's transparent, but also binds well with most common infrared substrates, including germanium, silicon, zinc selenide, zinc sulfide, fused silica, and chalcogenides. The structure of the diamond-like carbon is a combination of graphite and diamond, and it basically provides a thin layer of small diamonds across the surface of the infrared optic. So you can see here, this is a SEM picture of a diamond-like coating. It is anti-reflective, so that helps with the transmission, but it's also got good hardness and good stress resilience, and doesn't have too much of a loss in transmission. The nice thing about the DLC is that it can actually be adjusted to tune for very different spectral ranges in the infrared. On the material side, we're typically putting these coatings onto a variety of different materials. Silicon and germanium are probably the two most common infrared materials, but you've also got sapphires, zinc selenide, zinc sulfide, calcium fluoride, and our favorite, chalcogenides. Each one of these has a different wavelength range, but also a very different type of material. Silicon and germanium are metalloids, which means they act sort of like metals or semiconductors. Sapphire, the zinc selenide sulfide, and calcium fluoride are crystals, and the chalcogenides are an amorphous glass. So very different wavelength ranges, very different types of material. Our expertise allows us to work with all these materials, but also many other less common or exotic infrared materials that some people may use in optical systems. Looking at the transmission of these materials, you can see that they vary quite a bit in terms of wavelength range. These are all uncoated transmission curves for infrared optics. Once they're coated, they all sit at about 90% up here. But looking at the uncoated, it lets you see exactly where you may see issues. So for example, the silicon here starts at about 1.1 microns. It starts dying off around 9 microns, where something like chalcogenides work throughout the entire wavelength range all the way out to 14, 15 microns. But what you need to also consider is any IR material not only choice of it not only depends on the wavelength range, but also the optomechanical, the thermal, and the chemical properties of the glass itself. And this will go a long way in helping to decide which optical material or which combination of optical materials are used. And here at EMF, we have a large catalog of optical coatings, and as you see here, the infrared is broken up into many different sub-bands. So you have the SWIR band at 0.9 to 2.7 microns. You have the mid-wave IR, which is 3 to 5 microns. You have long-wave IR, which is 7 to 14 microns. And then you have a multispectral band, which is 3 to 14 microns. And EMF's catalog has a number of standard coatings, depending on the material and the wavelength range that you're working with. We also, in addition to just the material, we also have a number of environmental requirements that are typically quoted in terms of in terms of the durability and performance of the lens. So from adhesion, abrasion, humidity, solubility, salt spray, temperatures, and being able to wipe the lens without any damage. One of the nice features of EMF is that we have all the metrology for all these tests, environmental tests in-house, which is a key fact when looking for a manufacturer and being able to manufacture lenses quickly and reliably. Okay, so what we'd like to do is talk about the Chalcogenide family of glasses. And chalcogenides are glasses that contain one or more chalcogens, and those are sulfur, selenium, and tellurium. And they're all in the chalcogen group of the periodic table of elements. And these types of glasses are fast becoming a preferred optical material for infrared optics for a large number of reasons. Probably the biggest reason is that the lenses manufactured from chalcogenides are athermal. And what that means is that as the outside environment temperature changes, as you know, every material will expand or contract. And some materials like germanium will expand or contract so much that it will throw the lens out of focus. So the chalcogenides give an added great benefit in that they don't expand or contract as much, and as a result, they have a larger operating range and are able to withstand higher temperatures. So, if, for example, if you're going into a firefighting application, you'd want something like that to allow you to have a larger wavelength or temperature range. In addition, the use of chalcogenides with other materials allows lens designers to balance the focal shift over temperature so that the entire system can be athermal without having to do any mechanical athermalization. Secondly, relative to something like germanium, chalcogenides have a relatively low weight. And when you're flying these on a drone or on a helicopter, weight matters an incredible amount. So low weight is, of course, a key factor. Relatively low cost. Chalcogenides as a material probably cost about the same as other infrared optics, but the manufacturing processes allow you to manufacture them at a lower cost. And then finally, chalcogenides are opening up the market to high volume infrared optic production. Because not only can they be manufactured using traditional infrared optics manufacturing, which is grinding and polishing, diamond turning, or MRF, they also are opening up the possibility of being molded, which opens up high volume production possibilities for infrared optics. Now, all that's on the pro side. Some of the challenges that happen with chalcogenides is that you do see a lower adhesion between the glass and thin film layers than other IR materials. So the result of that is that it's a little bit trickier to get the thin films of the coatings, the anti-reflective coatings, to adhere to the glass. And we'll talk about that in detail in a few minutes. Secondly, it is much softer than other IR materials, so they need to be protected. In terms of actually holding them, they will chip or scratch a whole lot easier than something like germanium. And so if you are using them for an external optic, they do need to be protected using a diamond-like coating. Now, I've used the term chalcogenides and done this specifically because it's actually a family of glasses, and there are a number of different combinations of chalcogenide glasses. They have mixtures of germanium, arsenic, and selenium. This one is germanium, antimony, and selenium. This one's just arsenic and selenium. They're all chalcogenides because they all have selenium or tellurium, but they are known by different names and have different transmission curves through them. Basically, EMF can coat any of these types of glasses. We just need to know the specific glass and some of the specific points of information about the glass itself to make sure our coatings will adhere to that. In terms of spectral performance of our diamond-like coating, a lens that has diamond-like carbon coating on it actually has two different coatings on it. On the external side, we have the diamond-like carbon coating, and then on the internal side, we have a high-efficiency AR coating. And looking at the reflectance of both sides, on the high-efficiency AR, our reflectances are typically less than 0.3%. On the external side, the diamond-like carbon has a reflectance about 1%. So you will see a little bit higher reflectance on one side, but it makes up for the other. Okay, and these curves are typical for all the different optical materials in the infrared. When it comes through to transmission, we have two curves here. One is for a lens or a witness sample. One side is DLC, the other side is an AR coating, and as you can see, the transmission is above 90% throughout the entire long wavelength range, and it exceeds the industry expectations or standards with that. So in terms of actually putting these coatings onto chalcogenides or any substrate, there are four common coating issues. One is pinholes, stress, non-uniformity, and adhesion. And these four issues sort of dominated our thinking process as we developed the coating process and the equipment to do the coating. And this talk will go through how we have addressed these four issues with our process. Okay, the first challenge is our pinholes, and what pinholes are very tiny defects in the coating where the coating doesn't quite close up and seal the lens. So this is a specifically made optic made with transparent glass, but with the coating on top. And you can see where the individual spots where the coating didn't quite cover the entire surface. This was made in a traditional DLC chamber and expressly for the purpose of showing what pinholes are. Looking at them under an SEM, you can see that there are little divots in the coating that go all the way down to the substrate. And these are particularly dangerous because each one of those points becomes a possible failure point for this coating, meaning that some chemical can get into the glass and possibly start eating away at the glass, or some particle can get in there and start pulling the coating off of the glass. So every one of them is a possible failure point. And the whole idea of the coating is to protect the lens. So the idea would be to eliminate all the pinholes from your DLC coating. We use a proprietary PECVD, it's plasma enhanced chemical vapor deposition technique that deposits the carbon at the top of the chamber rather than the bottom of the chamber. And in this way, we are using gravity to assist us to make the best coating possible. Typically, DLC coating chambers have the optics sitting at the bottom of the chamber and the plasma coming down from on top. And the result of this is that some of the carbon settles on the sides of the chamber and then sort of falls off on top of the optic, causing a defect or an impurity on the optic. And that when the coating is all complete and the optic is cleaned, it turns into a pinhole. By coating up, we eliminate that possibility because any extra material falls to the bottom of the chamber and stays away from the optic, and improves the overall reliability and results in better performing optics. DRS Technologies, one of the leaders in infrared optics, has expressed that they truly prefer a DLC process that coats up to get pinhole-free coatings. The second coating challenge is stress within the coating. Now, stress, as you can see here, can actually crack a coating just on its natural stress levels within the coating. And where stress comes from comes from the deposition parameters of the different layers of the DLC coating, meaning that if the coating is deposited too fast or too slow, or the chemical makeup of the plasma is slightly off, the chemical bonds between the layers and the carbon atoms can actually pull apart the coating itself. So EMF has performed a great deal of in-house research to determine which parameters affect stress levels and then how those stress levels affect durability of the coating. We've gone through and adjusted the temperature, the pressure, the chemical deposition of the plasma, and given our history and know-how, we've gone through and fine-tuned our process. We've come up with the ideal setup of deposition parameters and process conditions inside the chamber, and be able to fine-tune the growth process that has low stresses while maintaining the durability that we're looking for. Third challenge is adhesion. Adhesion is basically the thin film being able to stay on top of the glass. And normally there's a chemical interaction that keeps it sealed and attached to the glass. In this particular lens, this is where there is a small adhesion defect, and you can see the coating actually peeling away from the lens. And this is a real danger for a number of reasons. One is it leaves the lens exposed, but two, I've seen cases where we have multiple elements and the adhesion failure doesn't happen until the entire lens assembly is all put together. And in those cases, you now have a foreign object inside your lens, which then can cause damage to not one lens, but multiple lenses or the mechanics that are inside. So it can really be a big issue if you have a coating that has poor adhesion. So the adhesion and getting a good coating is related to how the equipment is set up and the cleanliness of the parts being coated. And we've gone through and through our research, developed several steps to improve coating adhesion, specifically for chalcogenides because they are so difficult to coat. As we've talked about before, we've got the coating chamber design. We are coating up, which helps a great deal in reducing the amount of foreign object and coating defects. But we also have tight thermal control during the deposition. We found that this is one of the key factors in being able to get a DLC on chalcogenides that adheres very well. Combined with that, we have proprietary substrate preparation and cleaning for the lenses being coated. This is another key factor of making sure that the coatings are adhering to the optical substrate. We also found that the actual tooling that holds the optic in place while we're depositing material onto it, the design of that tooling is key in improving how the material is deposited onto the optic. So we've done a lot of research on that and have a tooling methodology set up so that we get the best deposition possible. And then finally, we have an extremely precise DLC coating design, that matches with the materials and the tight process control to make sure that it adheres correctly. So altogether, this ensures a successful adhesion on all IR substrates, and especially chalcogenides. The final challenge that we talked about was the non-uniformity of the diamond-like carbon coating. And here's a SEM of a coating that has a little bit of a uniformity issue. But basically, when looking at commercially available DLC chambers, we found that most of them have a rectangular coating area, but the plasma coming down is in a radially symmetric form. What we've done in our coating chamber is we've specifically designed the coating chamber to have a circular geometry so that the plasma cloud is radial symmetric with respect to the deposition plate. So basically, this is, in most cases in the commercial applications, you have a round peg and a square hole. We're matching the two together to make sure we get a uniform coating across the optics. So we'd like to know a little bit more about what your coating challenges are. If you have issues that, what's sort of your primary coating challenge that you're trying to address. And if you could take a minute to take the poll and be looking at the adhesion, uniformity, pinholes, or stress. And Robert, I'm having trouble seeing the polling results.
No problem. Let's have a look here. Okay, so it would seem overwhelmingly that it's adhesion that's most people are having a challenge with, and that's 61% of attendees. We've got the pinholes is another one on 20%. Uniformity is 7%, and stress is 11%. So definitely adhesion would appear to be the outright winner in that one.
Right, and one of the things to note is that adhesion itself can be caused by the other three. So it's not surprising that adhesion is sort of the overarching issue that most people have. Okay, so talk a little bit more about the components that go into our solution. We have developed a custom DLC coating chamber. When we started looking at everything, we wanted to sort of get things going quickly, and we were looking at commercial coating chambers, and none of them quite seemed to match what we wanted to do in terms of providing a solution to our customers. So we spent about 18 to 24 months designing and manufacturing our own DLC coating chamber. Again, it uses the plasma-enhanced chemical vapor deposition, is completely automated, and uses a circular geometry to match the plasma and to get our best uniformity. We're coating up to minimize or eliminate the pinhole issues, and we use advanced process controls to get us the type control we need for depositing onto chalcogenides. Finally, we also have, one of the other parameters is that we noticed that the position of the gas inputs and outlets have been maximized to give us the best coatings possible. So in terms of our whole entire process, and being able to coat chalcogenides, we've looked at these four issues, the pinholes and the uniformity. Both are addressed by our custom designed DLC chamber with the circular geometry and the coating up orientation. The stress and adhesion the solutions come from strict process control, a tightly designed coating, and some special tooling and a proprietary cleaning technique to reduce the stress and to get better coating adhesion throughout the entire process. So overall, this is our typical DLC coating. So like I said, on one side it's a DLC, on the other it's HEAR. So we're above 90% transmission, and here are the reflectances. And then here are the environmental requirements that that we go through to test our DLC. One is adhesion, where you apply a little bit of tape and pull it off quickly to see if the coating adheres. You have an abrasion test where you're rubbing the coating and testing it. We have a humidity test where we subject the lens to 90 to 100% humidity for 24 hours. Solubility is we'll actually immerse the lens into a salt water mixture to make sure that the coating is chemically stable. And then we also have a salt spray where the optic is exposed to a salt spray and fogging test. And then we temperature cycle it throughout the entire operating range of the lens. And in some cases, we'll do a wiper test to check the hardness of the coating. And again, all of this is done inside our facility, that way, if we do have any issues, we have a quick feedback to correcting them. But in most cases, the optics just sail right through all these environmental requirements. So as far as EMF as a whole, diamond lock carbon coatings are only one aspect of what we offer. We have diamond lock carbon coatings, and we also have a large catalog of anti-reflective coatings, not just for infrared, but also visible ultraviolet or any other, any sort of different combination that you need. We also do cold mirrors or hot mirrors where they're either transmitting or blocking the IR. We specialize in metallic mirrors, front surface mirrors for a variety of applications, including large format ones for telescopes. We also do oleophobic and hydrophobic coatings for specialty glasses, and can also coat onto plastics. And one of the things we pride ourselves on is the EMF Edge, which is high level of customer service, including on-time delivery, product quality, and incredible design experience, so that any sort of custom coating that you need, you are talking to the engineers before the sale and after the sale to make sure that that you're satisfied with what's going on. And then finally, we also offer some fast turnarounds, and once we get into production, we can set up a chamber reservation system. We do coat plastics, metals, glass, and ceramics, and it can go everything from prototypes to very high volumes, and are able to do extremely large optics in some of our largest chambers. So that concludes the talk. I'd like to open things up for questions. So I know, Robert, if you could jump back in and we can answer some of the questions.
Yeah, certainly. We've had a few. Thanks very much for running through that presentation, Ray. There's a couple of things that it seems to be jumping out. The first thing I was just going to ask was, does EMF offer other AR and or pro-tactic coating besides DLC?
Yes, we have a very large catalog of coatings. We've done over a couple thousand different coatings for different materials. So if you have something other than infrared, please give us a call and we can talk about what we have, or if not, we can design something custom for you.
And looking at those poll questions, is that the challenges that you were seeing, the percentages there, is that a fair reflection on sort of what you see as people coming to you with problems and the solutions you provide?
Yes, typically, a lot of in terms of applications, a lot of our customers are defense oriented, and they have some of the toughest requirements, specifically in terms of the environmental testing. And we're able to address those and actually provide the metrology to prove that the optics will work. And then in terms of the coding issues, adhesion is one of the top issues. Pinholes are another, and stress and uniformity are sort of secondary issues that may affect a specific application, but overall adhesion is probably the biggest issue overall.
And you mentioned that DLC is biologically compatible. Can you just expand and say what you mean by that?
Well, it doesn't really interact with biological systems, so you won't have any chemical interactions, or it won't affect any sort of biological systems. And in fact, DLCs are sometimes used to coat surgical tools, so that there's no interaction between the tool and the body being cut or dealt with.
What is the maximum size of optics that you can coat it with DLC?
With the DLC, we can coat up to a 14-inch diameter, and that's fairly large in terms of an infrared optic. I rarely see anything above 8 to 10 inches. So 14 inches is quite a large optic. But in terms of other coatings, we can go up to 108 inches. So that's quite a large range.
Yeah, absolutely. And with regard to the coating themselves, we've had a question here. Do you do multi-band IR coatings? Yes,
we do. Yeah. We've got some multispectral ones in our catalog, and then anything beyond that, if you send us your requirements, we can design something specifically for your needs.
There's also another question here. Is there an MIL or ISO test specification for the wiper test?
For the wiper test, usually no, I don't believe there is, but it's fairly common to see, a certain number of wipes, either 1,000 or 5,000, in setting that up. But we do have, we have made our own test, and if you like more details on exactly what we do, we can share those with you offline.
Do you view all chalcogenide materials similarly, or are some chemical compositions more problematic?
There are certain ones that are a little bit more difficult to coat, and a lot of it depends on the melting temperature of the glass itself. The IG6 type glass or IRG26 type glass is probably one of the more difficult ones to coat because of the low melting point of the glass.
And that's IRG24 as well?
Yes, 24 as well. Yeah.
We have a few more here to sort of quiz you with. What's the sort of normal turnaround time for sort of DLC projects?
In terms of actual coating, it takes about a week or two to get everything done. But that's providing that we have all the tooling and the fixtures that we need to do the coating. If we have to design and manufacture fixtures, it could be a few weeks in addition to that.
One other question we've got here is, why is there low adhesion between chalcogenides and thin film layers?
Because the nature of the chalcogenide glass, it's an amorphous material, and to get the thin film layer to actually adhere, you need to hit the right combination of temperature and pressure and it's an extremely narrow band of getting that right. If you're off just a little bit, then you end up with adhesion problems.
We have another question that's come in, which is, can you put DLC on tribological applications?
Yes, and what tribological applications are ones that deal with friction. So in some cases, people use DLCs to reduce the friction between two metal parts as they're sort of rubbing up against each other. And we do DLC coatings in that as well.
Great, okay. It looks like we're coming to the end of some of the key questions we've got here. I've got one which is, how coating at top of the chamber reduces pinholes. Can you elaborate?
Sure. It's basically pinholes come about because there's some impurity that is sitting on top of the optic that that then when you're done with the coating and you clean off the optic, that impurity sort of breaks off and you're left with a hole in the coating. So when you're coating at the bottom of the chamber with the plasma coming down, the plasma is not just hitting the optics, but it's also hitting the side of the side of the chamber. And then from the side of the chamber, it falls off and settles onto the optics. So by flipping it all upside down, flipping it upside down, the material goes to the top of the chamber, coats the optics, and anything that isn't adhering to the optic will fall to the bottom of the chamber and away from the optics. So in this case, we're using sort of a gravity assist to keep the impurities away from our optics.
Okay. Well, I think that has just about brought us to the end of all of the questions we've had coming straight in. I know there are going to be a few more questions there, and I think what will happen is someone from EMF, yourself, or one of your colleagues will be getting back to everybody else that can answer sort of any other questions that may come in. And of course, what we want to do is ensure that everybody that's attended can get in contact with Ray directly. So please feel free to reach out to him via the telephone number or the email address you can see on the screen. We're going to be sending out a copy of this presentation to everybody that's attended. And of course, if you've missed a presentation and you're not seeing this, then we'll make sure that you get a copy of the video as well. I would like to take this point to thank everybody that's come along and spent part of your day listening to Ray, providing us with some excellent insight into the challenges with chalcogenides. Ray, I'd like to thank you very much for taking your time to come on board and provide some valuable information.
Thank you for the opportunity. Thank you for the opportunity.
If there is anything else that anyone that's attending wants to reach out, you can always get through to myself. That's rob.fisher@optics.org, and we can pass on any messages to Ray directly. Alternatively, you can reach out to Ray through his email address and telephone number there. I hope everyone stays very safe and well. Thank you very much for joining us, everybody, and I hope to see you all again very soon for the next webinar. Thank you very much for your time.